Welcome back to linear algebra. In this video, we're going to be looking at the row and column spaces of a matrix. The idea of row and column spaces is going to give us a new tool for analyzing a linear transformation on vectors, also known as a matrix, in order to have a better sense of what kinds of solutions there might be to a system of linear equations. So, without further ado, let's get my head out of the way and dive right in. All right, so we have an arbitrary generic M by N matrix sitting here. If we analyze the rows of this matrix, each row has N entries in it. So each of the rows can be thought of as a vector in Rn. We can name R1 as the entries in the first row. To make it look like a matrix, or to make it look like a vector, I'm going to write it as a column matrix, even though what we're actually taking are the rows here. So the first row has A11, A12, down to A1n. The second row has A21, A22, down to A2n. And the mth row, Rm, has entries a M1, a M2, down to a Mn. And of course, the columns of this matrix are vectors in Rm. So we can name column 1. If I scroll up and take a look at it, right here we're taking the entries in a column, which actually does look like a vector. We've gone the other way often enough, taking vectors and writing them as the columns of a matrix. So we have A11, A21, down to a M1. We have column 2 as A12, A22, down to a M2. And it keeps going until we get to column N, which has entries A1n, A2n, all the way down to a Mn. With that simple annotation, we can now define the row space as the span of those row vectors. And we can define the column space as the span of the column vectors. Okay, that's fun and exciting, or something, I guess, maybe, sort of. It's not at all obvious that the row space of a matrix is useful. The column space is not immediately apparent, but thanks to a quick theorem, we can see why the column space is going to be useful. The linear system AX is equal to B is going to be consistent if and only if B is an element of the column space of matrix A. And the proof here, I'm not going to write out the proof in detail. But we can think of AX as a linear combination of the columns of A. If I rewrite matrix A as the column vectors, and I rewrite X as the column vector x1 through to xn, then the process of multiplying this matrix times the vector is going to be x1 times c1 plus x2 times c2 plus through to xn times cn. Right. That is literally a linear combination of the column vectors. The column space is the span of the column vectors, the set of all linear combinations of column vectors. So completely by definition, this linear combination must be in that span. And since we have the equation saying that this is equal to B, then this can only be equal to B if B can be written as a linear combination of column vectors, if B is actually an element of the column space. So that's why we care about the column space of a matrix. The row space is a little bit less apparent, but you can think of the row space as a lemma. We are going to find that it's actually easy to do work with the row space of a matrix, and we are going to come up with a couple of lemmas that allow us to link information about the row space into information about the column space. So that's why the row space is going to be useful, because it will help us find information about the column space. Two matrices which are row equivalent have the same row space. And I need to stress this, it's not actually part of the theorem, but two matrices which are row equivalent are going to not have the same column space. Row equivalent matrices very often have different column spaces. It's possible to have the same one, but usually not. So I need to stress that as we get started. We can use elementary row operations to make it easier to work with the row space, but it doesn't do anything for the column space, or at least not directly. Once again, I'm not going to give a full proof here, but I want to jot down a couple of ideas that will help you understand why this has to be the case. We know that the row space is the set of all linear combinations of vectors of rows, row vectors, if I can talk. And linear combinations of rows is exactly what the elementary row operations do. Swapping two rows, well, that doesn't really do anything to the set of row vectors. Changes the order, so it might change the way we denote the linear combination, but the linear combinations will all be the same. Multiply a row by a constant. Well, it just changes the constants you need in the linear combination, but it's still the same linear combination. Add a multiple of one row to another row. That's literally taking a linear combination of two of the vectors. And since we are looking at the set of all linear combinations of linear combinations are still just linear combinations. So again, not really a full proof, just a sketch of the idea of a proof, but hopefully enough to convince you that two matrices which are row equivalent will have the same row space. And having that allows us to build up this next theorem. If a matrix R is in row echelon form, for convenience, we will generally take it all the way to reduced row echelon form, although technically we don't need to. Row echelon form is enough. But as soon as we get to row echelon form, the rows which contain leading ones will form a basis for the row space. I'm not even going to try to write down a proof of this theorem, but it should at least make some sense to you when you think again about the fact that elementary row operations are taking linear combinations of vectors. Essentially, what the elementary row operations are trying to do in terms of vectors is find the linear combinations which give us the zero vector and get them out of the way. Because zero vectors don't belong in a basis. The zero vector is not linearly independent of anything else. So if we can get rid of those zero vectors, and we can get rid of any way of finding linear combinations that produce a zero vector, then what we're left with is a linearly independent set. And if we have a linearly independent set, and that set spans the vector space, then we have a basis. So instead of looking at a proof, let's take a look at an example. Let's consider a kind of nasty looking matrix. Here we go. 1, -3, 4, -2, 5, 4. 2, -6, 9, -1, 8, 2. 2, -6, 9, -1, 9, 7. And -1, 3, -4, 2, -5, -4. We want to find a basis for the row space of this matrix. And so to do that, our goal is going to be to rewrite this matrix in reduced row echelon form, or again, just row echelon form technically is good enough. There are a couple of ways you can get started, but what I noticed right away in this matrix is how similar the first and fourth rows are, and how similar the second and third rows are. So the first thing that I want to do is take row 4 plus row 1 and take row 3 minus row 2. So the first two rows stay the same. Third row minus the second row. 2 minus 2 is 0. -6 minus -6 is 0. 9 minus 9 is 0. -1 minus -1 is 0. 9 minus 8 is 1. And 7 minus 2 is 5. Then the fourth row plus the first row. -1 plus 1 is 0. -3 plus 3 is 0. 4 plus -4 is 0. -2 plus 2 is 0. 5 plus -5 is 0. 4 plus -4 is 0. So satisfying. All right. We are incredibly close to row echelon form already. Just take that second row minus twice the first row. That will get rid of the first term in the second row, and then we'll figure out the rest from there. So the first row stays the same. Two minus 2 times 1 is 0. -6 minus 2 times -3 is 0. 9 minus 2 times 4 is 1. -1 minus 2 times -2 is 3. 8 minus 2 times 5 is -2. And 4 minus 2 times 4 is -6. Third row stays the same. Fourth row stays the same. With that, we are in row echelon form. We are done. Right. We could take this to reduced row echelon form if we would like, but row echelon form is good enough. And now we have our matrix in row echelon form. Every row starts with a 1. Everything below that 1 is a 0. And everything to the left of the 1s is 0. So we have an entire 0 row. 0 rows are not rows which contain leading 1s, so they are completely out of the basis. The basis for this particular row space will contain 3 vectors, R1, and I'll write it as a column vector because that's what we usually do with vectors. We have R2. And we have R3. Written just like that. All right. The column space is much less intuitive. And it's really not worth the time to dive into how and why we know this works. So I know it's always unsatisfying to get a theorem without proof, but the columns in matrix A, which contain a leading 1 in the row echelon form of A, form a basis for the column space of A. To try to make sense of that, let's jump into the specific example of the matrix we were just looking at. So to get some space to work with it, let me copy my matrix and its row echelon form down here onto a new screen. Let's get some of this excess out of the way, and let's move this over so that things line up a little bit more nicely. So here I have matrix A, and I have, I'll call it matrix R, the row echelon form of matrix A. And we know that this had 3 leading ones. The columns which contain these ones form a basis for matrix R, which is nice but not really helpful. The theorem tells us that if we take the corresponding columns of matrix A, these form a basis for the column space that we care about. So I can take vector C1 will be the column 1, 2, 2, -1. I can take column C2, 4, 9, 9, -4. And I can take column C3, 5, 8, 9, -5. These 3 columns, because they map to those leading ones in the reduced row echelon form, or just the row echelon form, these 3 columns form the basis of the column space. It's a roundabout way to get there, but it does get there, and that's what really matters. And again, remind you, why do we care? We care about finding the column space because the column space tells us what systems of equations have solutions and what systems of equations do not have solutions. We care about the row space because the row space helps us find the column space. Let's phrase this a little bit more nicely. Consider an m by n matrix A. Based on what we just saw, it must be the case that the row space and the column space have the same dimension. That falls directly out of our theorem that we just used. We take the matrix, we turn it to row echelon form, we identify all of the leading ones in row echelon form. The rows with those leading ones form the basis for the row space. The columns with those leading ones form the dimension for, or form the basis for the column space. Since there's the same number of leading ones no matter which way you are looking at things, and since row echelon form tells us that a leading one must be unique in a row and unique in a column, then these things have to have the same number of vectors in each basis, so they have the same dimension. We will call that dimension the rank of A, and literally write it as rank of A. Interesting, quick thing about rank that's actually going to come up again later on in the course. The rank of A is less than or equal to M, and the rank of A is less than or equal to N, where M and N are the number of rows and the number of columns in the matrix. And again, that should make sense. If there are M rows in a matrix, then best case scenario, the row space has dimension M. There are M vectors, some of which might be linearly dependent on the others. So the dimension of the row space is M or lower. Likewise, there are N column vectors. So the dimension of the column space is N or lower. Fairly straightforward theorem, not very satisfying. But like I said, that's actually going to be something that comes up again in the next video. That's it for row and column space, and I'll see you next time.